how to model, how to conceptualize this process with data structures. So previously in queues, in-queue process is just having with an element. So there was nothing about the priority, right? And there is no operation related to priority. However, when we turn the queues into priority queues, now in priority queues, in queue an element, we have to add priority, right? So these persons, these three people, have a priority, lower priority, and this particular person has a higher priority. Means that the element associated with priority numbers, right? So priority in the priority context, in our definition, let's say that higher value has higher priority, lower value has a lower priority. For example, these three persons have 0 priority, and this particular person has 1 priority. This priority value is bigger than 0, so this person has a higher priority, and this person should get off first. Let's imagine that. So consider the following example. Professor Taylor has priority 2, and the professor of these three people have priority 1. In that case, this person has the niche, right? And therefore, the interface, the course method course structure, method signature should change as following in the follow. The priority queue will be in queue element, not only with the element, but also with the priority numbers. Rather than in queue element, only with element in queue. This is not going to happen, and this is going to happen in priority queue, right? So this person has a higher priority, these three people have lower priority, and this person gets in the line even though he arrived at the late, the most latest in the queue. So for this particular example, FIFO, F-I-F-O, first in, first out, is violated. All right. So how to implement priority queues? At this moment, I think that you are have pretty good knowledge how to implement this with linked list, right? So using the linked list as the basis of the priority queue, because this is another basis for the queue. So store the element as well as the priority. So store the two values in a linked list node. So that's one thing that will happen, right? And for this particular linked list basis, you can implement the priority queues in two ways. And the first way is called lazy approach. Lazy approach is called unsorted implementation. So what happens is that when there is an in-queue event, just insert the element and the priority with it at the end of the queue, right? So in the previous example, obviously it's not the lazy approach, it's an early bird approach, right? So lazy approach, so is this in queue Professor Taylor, right? Even though that happened, we are not putting him at the front. Rather, we treat this node as usual. But the different thing is that we store it with priority value as well. So, so this is the just normal queue at this moment in the in-queue process. It's just a normal queue. However, something different happens in the dequeue process. In the queue process, remove the element with the highest priority by searching the queue from the beginning to the end. So basically, this is a linked list. So we can start from head, move and get next, move to the tail. That we can do, right? And then what you want to do is that we search through the values with the and search that if anyone has the higher priority, and search through it. And if the search does not result in a node with higher priority, then just the dequeue process as usual. However, by searching through from head to tail, we find that a certain person has a higher priority. In this case, just dequeue it first. So after dequeuing proprietary, the queue will look like this. And that's what happens in the RAGE approach. On the other hand, the early bird approach looks like this, right? This is an unsorted implementation. So it's not sorted by the priorities, right? However, in the early bird approach here, what happens is that the picture that we saw in the earlier example, right, is a sorted implementation. So when there is an in-queue event, whenever in-queue happens, insert that element with priority at the position that starts a sequence of elements with lower priorities, right? So whenever we try to in-queue Professor Taylor with higher priority, we put that higher priority person at the front of the queue. That's what happens. So in the in-queue process, this will have to do some kind of going through and searching through an in-queue process. That's what happens. And in the dequeue event, because that prioritized element is at the front of the queue, you can just remove the element at the front in the line, front of the queue. And this is called the sorted implementation, because that whenever at the in-queue level, this is sorted by the priority, right? This is sorted by the priority. And because of that, it's called sorted implementations, and this is called unsorted implementation, right? So these are the two approaches how to implement the linked list, how to implement priority queue with the linked list. So you can put the priority queue implementation in the in-queue process or in the dequeue process. In the dequeue process, if you put that code in it, in that case it's called RAGE approach, because that you are holding it until you dequeue it, right? So it's kind of lazy operation. However, early bird operation, kind of diligent operation, is that whenever you in-queue it, you just put it in, right? And then whenever you want to dequeue it, then you don't have to spend time there, right? So it's called early bird approach. And this is kind of particular example of the priority queues, right? So it's sorted implementation, right? And in queuing operation, so this is called sorted implementation as well as the early bird approach, right? So in-queue operation happens here, right? So in-queue current head, while priority is bigger, right? Then priority just get next. And whenever the priority is right, priority is at the right position, then at that point you insert it, right? That's what happens. So here you have in-queue operations, and this for loop will search through the right position. And if the node get value is equal to like this, in the case that's the tail, that's the blank and tail of this linked list, and you are going to insert at the position. And if it is not tail, it must have some priority. And if that priority is lower than the current node's priority, in that case, it's the time to insert it, because that we are taking the early bird approach, right, or sorted implementation. In the other case, we just increase the search index order, right? And then after you determine where to put, where to insert the node in the linked list, then you perform the insertion operation here. Because this is the sorted implementations, the queue operation is quite simple as in the queue, right? So unsorted implementation in this case, in queue is going to be short like this, and the queue is going to be way longer in these implementations, right? And to hold the priority value, you have to modify the node a little bit, and now it's called priority node, and it's going to hold value as well as priority value, like this. And this is how it runs, right? So this is how the actual code of the implementation. I'd like to hold this video, build the lecture for a moment, and for you to have time to implement this short code. It doesn't take long time to type in because it's pretty short. Alright, so you implement this, that's very nice, and let's move on. So here we see this picture again. However, in this case, we are going to argue a little bit about the priority sense, right? So, performance of the priority queue implementation is this. So we have the unsorted implementations and we have sorted implementations. That's we have covered so far, right? And we have up to this point, we have these operations. So in queue operation, unsorted implementation in queue is just putting at the rest of the line. That's what happens here, order 1, order constant. Sorted implementations might have to search through all the list. In that case, to find the right position to insert it. So it will take order of n. However, and it's called the early bird, and this is lazy. And because of its lazy approach, whenever we want to dequeue it, it will take order of n time. However, we already sorted the linked list with priority, so in the dequeue process of the sorted implementation, it will just take the order of constant. And find the highest priority actually is the right. It's the dequeue process is going to be same, right? Having said that, up to this moment, this is the linked list based approach. Just like this, linked list based approach. However, we know that we can reduce some time by utilizing these tree-based operations. However, we haven't found any way to implement priority queue with tree-based structure, and actually it is possible, and actually it's coming to the second part of this week. It's going to be called binary heap. So binary heap is a tree-based implementations of the priority queue. So tree-based implementation of the priority queue is actually the heap structures, right? So it's natural to have these heap structures in the second part of this lecture. And to enable this, order of log n, order of log n, order 1, without adding condition saying that this tree structure is in average, not in worst case. Without to say this performance, without adding this condition, we have to make these tree structures like this tree. It shouldn't look like this worst case. It shouldn't look like this worst case, right? So we are going to call this nice looking tree structure as balanced tree. And these bad structures, we have whole empty space which is not utilized here, and it's going to be called unbalanced tree. And this balanced tree doesn't have so much hole here. It has hole only here. However, unbalanced tree has a huge big unutilized space in these tree structures, and in this case it's going to be balanced, and this tree is not going to be balanced, right? So how to find out the balance or not balanced? Before we go further, so this particular implementation doesn't have any condition in it. Tree-based implementation in average or tree-based implementation in balanced tree, we don't have that condition. It's just tree-based implementation. Means that this binary heap, these heap structures, is always going to be balanced, right? And the whole point of the second part is how to make tree balanced. And that's the whole part of this lecture, of the second part.